All right, guys. I welcome you to this biology class. The last time we had biology was last week when I was discussing the cell theory, and the class didn't go as smooth as I had planned due to network. A lot of people said they couldn't get me, but um, I have a recorded class on the cell theory, so I'll share it with you guys after this class is done. So. Someone has unmuted themselves again after I muted them. Miriam and okay, so let me just mute everyone. Okay, so I'll share the class on the cell theory, and when we are done with water, we'll talk about cell division. But as of today, let's concentrate on this topic known as water. So I'm sure this is not a new term that we are hearing for the first time. We've been talking about water ever since time immemorial. Since you were just kids, you knew to say there was water. Even in grade one, people knew to say water is life. But how is water life? Okay, and that's what we're trying to discuss today. What makes that statement valid? The statement we used to say when we were kids to say water is love, is life. I wanted to say love, right? But anyway, it can be love. It depends on how you define your love. Okay, so we're trying to validate that statement to say how is water life or how is water important to the environment and what makes it very important to the environment. As we know, uh, water has a lot of unusual properties, properties that are very unique as compared to a lot of other small molecules that have almost the same mass as that one of water, but it just decided to segregate itself and possess a lot of different or rather unique water properties. And that's the reason, or that will be the main focus of our discussion today to look at those uh, properties. Okay, so as you know, water is important in many ways. Especially in the human body, you understand to say 70%. By now, you know to say 70% of the human body is made up of water, which means each and every activity of the cell in the human body requires water. And how or why only water? Why is it that water is the one that is functioning like that? If you look at a lot of aquatic life in oceans and seas, how are they able to survive in different circumstances in that water? That's what we are trying to look at. We'll see the reason why God included water in your body and not paraffin or not any other liquid, petrol, or what else. You'll see why we chose water. So I'll have a simple question for you. What makes up water? Anyone who has an idea, what makes up water? Anyone who can give it a try? These are questions that even waking you up at, I don't know, 03, even if you slept with hangover or if you slept drunk, you should be able to answer such questions, eh? What makes up water? Oh, you have muted us. Yes, I have muted you because you are unmuting yourselves unnecessarily, even when you are not asked to do so. So you can just type hydrogen and the oxygen. Okay, so water is made up of three atoms. You can see how simple water is. It just contains three atoms. It has one oxygen molecule and the two hydrogen molecules. And these guys they are covalently bonded to each other, and they form a bond angle which is 104.5 degrees between the two hydrogen atoms whilst they are connected to the oxygen. So that is one of the most important things you're supposed to take note of. It's the bond angle that is in existence in a water molecule, because those are the kinds of questions that they like a lot when it comes to what? To multiple choice questions. So let me just do this. I show you the structure of water. Okay, structure and properties of water. So those are some of the properties, and this is the structure of water. So you can see how the atoms are bonded to each other. And there's also another question that they like asking to say, why does water make a V shape? I've told you to say water is not linear like most molecules are. You find that a lot of molecules, when bonding to each other, they are just linear or in a straight line. Find that maybe it's just that hydrogen connected to oxygen, but in the case of water, it forms this V shape. It is a bent molecule like that. And this bond angle that exists here, we say it is 104 0.5 degrees like that. So another question that I'm going to ask you is why does water form that bond angle of 104.5 degrees? Anyone who has an idea? Okay, so I've unmuted you. Those who want to talk, you can now unmute yourselves. Those who have an idea, why does water make up that bond angle of 104.5 degrees? Okay, so this is mainly due to the orbitals that are in water. Those who are registered, I'm sure you've seen on the drive, there's a video on atomic theory or atomic structure. And I explained what orbitals are and the role that they play in terms of chemical bonding. So here you are forming two covalent bonds with the hydrogen molecules. And the or this oxygen molecule, when it bonds with hydrogen, it actually leaves two lone pairs of electrons. What do I mean by two lone pairs of electrons? It's those electrons that are not taking part in the chemical reaction. Remember, oxygen has 6 electrons in its outermost shell, and only two of those are taking part with the formation of the covalent bond. One with this hydrogen, which is here, and another one with this hydrogen, which is here. And so it leaves 4 other electrons that are not taking part in this chemical bonding. So those four electrons, they are also paired. They are known as lone pairs of electrons. And they are the ones which repel the ones that are bonding, or repel the orbitals or the electrons that are taking part in this chemical bond. So since the bond or the repulsion that they possess towards the bonding electrons is much more than the repulsion that these two bonding electrons will be possessing on each other. That's why you're going to find that the oxygen molecule is actually bent to one side. It is forming a V shape on one side. They are forming an angle of 104.5 degrees, and that is because of the repulsion that is taking place between the non-bonding electrons and the lone pairs of electrons. Are we together there? Yellow.
Yes, we are.
Okay, very good. So that's about the shape of water. I don't think they can ask you more about the shape or the bonding that is taking place. I've already explained what we are talking about. So that's still the
Excuse me,
structure.
sir.
Yes.
Can you kindly repeat what you said, like about the 104.5 degrees?
Okay, so I've said when the two hydrogen molecules connect with the oxygen molecule, they don't form a linear molecule, or let's say a straight molecule like this. Water is not like this. Maybe some might think it is a linear molecule, which is just having oxygen on the middle like that. This is not the shape of water. The shape of water is a V shape, like this one that I've drawn here. Now the question is, why are we forming the V shape? Because this shape when it is formed, the angle that is between the two hydrogen molecules here, we call it the bond angle of water, is 104.5 degrees, or some literature in some books you'll just find it as 105 degrees or 104 degrees. Just make sure to say the average number or the overall number that you're going to talk about is around 104.5 degrees. So what is causing this bond angle? Why is the molecule not linear? That is due to the lone pairs that are present in the oxygen molecule. Oxygen has 6 electrons in its outermost shell, and the valence electrons in the outermost shell are the ones that are taking part in the chemical bonding. So, 2 of those 4 are the ones which are going to pair with one hydrogen, and the other one also pair with one hydrogen, leaving 4 other electrons that are not taking part in the chemical bonding. Okay, so those 4 now, they are already stable. We call them lone pairs. So we're remaining with the 2 lone pairs of electrons. And what do they do to these electrons that are taking part in the chemical bonding? They repel them. They are going to be located on this side like that. You have 2 electrons there and 2 other electrons there. They are going to repel. They'll be producing a repulsion force towards these electrons that are taking part in the chemical bonding. And this repulsion that is here is much stronger than the repulsion that is going to be between these two uh, electrons that are taking part in the chemical bonding. And that is why the molecule of water is having a V shape in that manner. It's due to that simple fact, and thereby leading to that bond angle which is there. Is that clear now?
Yeah, thank you.
Okay, very good. So, um, one other thing that I want you to know is that water actually is a polar molecule. One of the most notable characteristics, or one of the most important characteristics of the water molecule is that it is polar. And what is causing the polarity between the water molecule or in the water molecule is the electronegativity or the difference in the electronegativity between the two or the 3 sets of atoms that are taking part in the water molecule. If you check out or if you've had time to look at the periodic table, you're going to agree with me to say, as you go towards the right of your periodic table, the electronegativity of the electrons also increases. What do I mean by that? Who can define electronegativity for me? Who can define electronegativity for me?
This is the ability of an atom to attract electrons.
Very good. So, the ability of an atom to attract electrons more to itself than sharing them equally when taking part in a chemical bond. So, molecules that are on the far right of the periodic table, we say they are more electronegative as compared to the electrons that are on the far left of your periodic table. And if you check hydrogen, theory says it is in group 1 of the periodic table, although there are some question marks around that statement. But yeah, most of the periodic tables that you're going to look at, they are going to display hydrogen as a group 1 element. And if you check oxygen, what group is oxygen?
6.
Okay, so oxygen is in group 6 and it is more electronegative. It has a higher electronegative or electronegativity as compared to the hydrogen. And that leads to the unequal sharing of electrons in the water molecule. Oxygen wants to own those electrons more to itself than it wants to share it equally with the hydrogen molecule. And due to that fact, you're going to find that partial charges are going to develop on the water molecule. We call them partial charges. They are not complete charges. Why? It's because there is still sharing of electrons. It's not a complete transfer of electrons like in an ionic bond. They are still sharing, but the only problem is that oxygen is being selfish. It is more electronegative. It wants to own them more than it wants to share them equally with the hydrogen molecule. So as due to that fact, now you're going to find that this oxygen here, which is bonded to two hydrogen molecules, that one and that one, this water molecule here with its bond angle there is going to develop what we call partial charges. And we represent those partial charges by a delta to show that they are partial. So hydrogen, since it's the one which is being disadvantaged, it's more like it is almost losing the electrons. It is going to develop a partial positive charge. Even that one is going to develop a partial positive charge, whilst the two partial positive charges are going to be balanced by two partial negative charges that are going to develop on the oxygen atom like that. Are we together?
Yes.
Okay, so this now is what leads to more of or most of the unique properties of water that we are going to discuss in our lesson. They are due to this fact, the electronegativity and the unequal sharing of electrons and those partial charges. They are the ones that are surrounding most of the theory. Most of the theory that is surrounding the water molecule. Rachel, you have a question? What is your question again?
My question is, I'm kindly asking if you can repeat on the partial charges.
Okay, so I've said,
Can you get me?
yes, I can get you.
Uh,
Okay, so I've said, the partial charges that we are seeing here, it's due to the electronegativity difference between the two atoms that are taking part in this chemical bond, or rather the three atoms. I'm saying two, it's because it's two different types of atoms. So, the oxygen atom is more electronegative, or oxygen is more electronegative compared to the hydrogen molecule. Electronegative. Someone is writing on my screen. What is going on? Whilst the hydrogen is less electronegative. So the electronegativity, someone has just defined electronegativity for us to say it is the ability of an atom to pull electrons towards itself more than it can share them equally with another atom that is taking part in a chemical bond. And that is exactly what is happening in this water molecule. Oxygen is more or far much electronegative than the hydrogen molecule, which is in group 1. So when they start sharing their electrons, oxygen wants to own these electrons. It pulls these electrons towards itself more than it wants to share them equally with the hydrogen molecule. And that is what is leading to the partial charges that are developing on the water molecule. So since hydrogen is more on the disadvantaged part, whereby it is more like it wants to lose those electrons, but it's still sharing, but not equally. It is developing a partial positive charge, like this one here. Here and there. You have two partial positive charges developing each on the hydrogen molecules. Whilst to balance these two partial positive charges, what is happening? Two partial negative charges are also developing on the oxygen molecule, and that is what is causing polarity in this atom, or in this molecule rather. Is it clear, Rachel?
Yes, sir. Thank you.
Okay, very good. So, now that we've looked at the introduction to our water molecule, we can now dive deep into some of the characteristics that I would love us to discuss, uh, the unique characteristics that I want us to discuss about on this water molecule. So, anyone who can give it a try on the characteristics of water molecules? I would love to hear someone say something. Anyone?
Water is solvent.
Wait a bit. The unique characteristics of water, like that. Okay. The first one, what did you say?
Water is a solvent, meaning it can take part in any chemical reaction.
Okay, so to satisfy that statement, we say water is a universal solvent. Okay, so that is the first one. Very important one. Another one? Another one? Anyone else who can give it a try? Guys, just say whatever is in your mind. We don't lie in science, so long as you can back up your answer.
Sir,
Yes, yes. Someone is trying
what's
to
the
say
difference
something.
between characteristics and I'm asking a question.
Yes.
What is the difference between characteristics and properties?
Properties of water, characteristics. It's one and the same thing.
Uh, okay, sir.
Yes. Anyway, you
Okay.
want me to change the heading? I wrote this, but
No, I just wanted to know.
oh, all right. No, don't get confused. That's what I'm looking for. I'm looking for that same thing, the unique properties of water. And those are the things I want you to say. But I just wrote that. Even in my notes, I have properties. I don't know why I wrote characteristics, but that's what I'm looking for. Yes, someone was trying to say something. You can go ahead.
Okay. Water has high heat capacity.
Very good. So water has a high heat capacity. Capacity. Okay, this is the second one. There are actually 10, so I'm expecting you to mention all 10 of them.
Okay. Water is neutral and has a pH of 7.
Okay, water, the pH of water, it's approximately, so I'll put approximately, because it's not all the time that you find it like that, but let's put 7. Anything else? Okay, so water is dipolar in nature. Another one, water molecules tend to stick to each other. Okay, and anything else? Anything else? Okay, so water molecules form, or water forms hydrogen bonds. And the next one will say has high melting and boiling points. Anything else that you remember?
Cellular processes.
Okay, can you tell us more about the cellular processes? What do you mean? Okay, whilst you are thinking about that, we'll say water has or exhibits cohesive forces. Are you telling me you've never heard of these things I'm writing here, or you just want to be quiet? Very bad students, huh? You don't want to talk. Sure. Okay, so water also exhibits adhesive forces. Adhesive forces.
Maybe I try another one.
Yes.
Water has a low density.
It has low density. Are you sure? That is a very blank statement, eh? What has low density? What has
Low density as a solid.
Okay, we'll talk about that. Yeah, you are correct now. Because the density of water keeps on changing. So if you say water has low density, it's more like you've just given us a blank statement. Okay, so we also, water has high latent heat. Heat of vaporization. Okay, and I think this is all. Are they 10 now? Okay, and the last one we'll talk about is density properties. Density
So
and freezing. Yes.
I don't know if we can add this point there, but what about the freezing point? If
This
we
is
just
what.
say like the freezing,
Yes, the
if we
freezing
could just
point.
say like if we could just say the freezing point of water is 0 degrees Celsius, can you put that under properties of water or what?
I was actually going to discuss about it, but I am not including it on the unique properties of water. But water has a high melting and boiling point. That's where all that information you're talking about is going to fall under. It's because the freezing point and the boiling points of water are going to be mentioned in that statement, in that, or yeah, in that umbrella. I can say that. Because if you go up, you are boiling. Even when you start cooling down, you are going to see that the melting point and the freezing points of water are actually very high compared to some other different molecules that are almost having the same mass as water. As you are going to see, I'll continue comparing water to some other molecules that have almost the same mass with it, but you're going to see the difference, how big the gap is in terms of such characteristics, the boiling points, the melting points, the freezing points, and you'll see why water is very ideal for the human body. Okay, so
Okay, say my last question.
yes.
Okay, what about this point, like the last one? What if we say like water is transparent?
Water is transparent. That wouldn't be a unique property enough because a lot of other liquids are also transparent.
Oh, all right.
Yes. Okay, so water is a universal solvent, but I won't start with this point. I'm going to start by explaining the point which is causing most of these unique properties that I've written down here. And the first one is that water is dipolar in nature. So, why are we saying water is dipolar in nature? I've already explained about polarity to say we are forming a dipole moment on the water molecule by developing the partial charges. And those partial charges, if a more electronegative element forms a bond with a lesser electronegative element, they are called or they form what we call a polar molecule. But if you look at the water molecule, it has not one dipole or not one partial charge, but two of them. And since there are two separate partial charges, we call it a dipolar element or a dipolar, what do we call it? Uh, hey, a dipolar molecule. Yes. So these two sets of partial charges that we have here, even here, are what are making this molecule dipolar in nature. And that is all due to the difference in the electronegativities of the two different atoms that are present in the water molecule. Okay, so we'll say water is dipolar in nature, like that. And it is because of this polarity now, the dipolarness, that water molecules also are going to be tending to stick to each other. If you get let's say a cup or a bucket of water, you can't tell to say there's a single water molecule there with your naked eyes unless otherwise with some magnification tools. But water molecules, how they behave is that if you have more water molecules, they get attracted to each other. And what makes them attract to each other is these same partial charges that are here. Because you understand to say if I have another water molecule here, like that, it is also going to have two partial positive charges and the two partial negative charges like that. So what is going to happen is that the opposite partial charges now, they start attracting to each other. And by them attracting to each other, you find that this partial positive or partial negative oxygen molecule is going to get attracted to the partial positive hydrogen. Let me just clear this. Okay, so this partial negative oxygen is going to start to get attracted to the partial positive hydrogen, because I know it's not your first time today hearing to say opposite charges attract each other, and it is the same theory that is applying here. The partial positive charge of this water molecule is going to attract the partial negative charges, which is the oxygen here is the one which is partially negatively charged. They are going to attract each other and they are going to form this weak bond, and thereby sticking to each other. These molecules are going to be stuck to each other, and by so doing they are forming this weak bond which is here that I've drawn in green here. And what do we call this bond? Anyone who has an idea? What do we call this weak bond that is forming between the partial positive and the partial negative charge?
I just want to try.
Yes.
Maybe they are ionic bonds.
Okay, but not quite really, because an ionic bond involves the transfer of electrons, and there's no transfer here. It's just two charges, opposite charges attracting each other and forming that weak bond here.
Sir,
Yes.
I think like it's metallic bonding. the flow of charges, the positive and negative charges.
Yeah, not really again. I've already mentioned the answer. In fact, when I was writing, I mentioned the answer. Someone is making noise. I don't know who. Kasonda Rita, you're making noise. Okay, so this bond, guys, is what is known as the hydrogen bond. You haven't done chemical bondings yet?
No.
No.
Oh, I'm really sorry. So this bond that forms between the partial positive charge and the partial negative charge is what we call a hydrogen bond. It is just a weak bond that forms between two polar molecules, and these two molecules of water, they are polar, and they're going to start attracting each other, and that's what we call hydrogen bonding. Are we together there?
Yes.
Yes, so I'm sure when we do chemical bonding, they'll explain more on this one. Now the problem is that some people's syllabus they don't cover atomic structure and chemical bonding. They just start from the molecular biology. So anyway, that's that. We have explained to you to say this is what we call a hydrogen bond. It's not that it's only taking place between a hydrogen and a hydrogen. No, it's taking place between two polar molecules. It's a weak bond forming because of those attractions due to the difference in the electronegativity. So this hydrogen bonding now overall, if they ask you now to say what causes the unique properties of water, it's because of the dipolarness, and this dipolarness is leading into hydrogen bonding. Hence, hydrogen bonding is going to be leading to different now characteristics of these water molecules. They like such questions sometimes in multiple choice, but yeah, it's
Sir,
that's that. Yes.
sir, repeat your statement.
Sorry,
I'm saying read your statement.
your network is bad, but I've heard what you've said. So I've said overall now, if they ask, say, what causes the unique properties of water? What is the mastermind between the unique properties of water? It is due to, yes, we know to say there is dipolarness, and this dipolarness is leading to the attraction between the water molecules, and this attraction is known as hydrogen bonding. So the presence of hydrogen bonds between different water molecules is what causes the unusual properties of water molecules. Are we together there?
Yes.
Okay, so let me label this bond in case of cases. It's a hydrogen bond. Like that. Okay, so that's a hydrogen bond. Let me check these notes if they've shown the bond clearly, or clearly, rather. Clearly. Okay, so a lot of water molecules. So I've said water molecules tend to stick to each other. So this is what I was talking about. If you can look at this picture, or this picture which is in the notes. Oh, I'm trying to reduce the size of the picture. Yeah, so if you look at this picture, a lot of water molecules are sticking to each other due to the polarity. Okay. Polar molecule. Do I have a hydrogen bond explained? No. Okay, dipolar. I've seen hydrogen. Okay. No. Okay, I can't find what I'm looking for, but it's fine. I just wanted to show you a hydrogen bond in a picture, but it is the same one as this one that I've shown you in green here. Okay, so apart from hydrogen bonding now, what other character or property is this hydrogen bonding going to lead to? It is going to lead to water having a very high boiling and the melting point. So if we look at the water molecule, let me start from here. Okay, so like that, high melting and the boiling points. Okay, so if we look at this statement, water has a very high melting and boiling point when you compare it to other simple molecules that have almost the same mass with it. Some of the examples that I can give is methane. In chemistry, grade 12, in is it organic chemistry? I don't know. You talked about methane, and it had a chemical formula of CH4. So you can see carbon and hydrogen, there is no difference in electronegativity. Hence, this molecule is not polar. The other one is ammonia. Ammonia, I'll say it's NH3 like that. And also hydrogen disulfide, which is H2S. So if you look at the boiling and melting points of these guys, you're going to find that their masses are almost the same. The mass of water is 18. Oxygen has 16, hydrogen has 1, and the other one 1. It is forming a molar mass of what? Or a molecular mass of 18. If you look at the mass of methane, it's 16. NH3, it's 17, whilst the hydrogen disulfide, it's 34. But if you look at the melting points and the boiling points, they are very different. The melting point of water is 0 degrees Celsius. The melting point of methane is negative 182 degrees Celsius. The melting point of ammonia is negative 78 degrees Celsius, whilst the melting point of H2S is negative 60 or negative 85 degrees Celsius. So you can tell this difference. If you compare the melting point of water to these other molecules which are having almost the same mass as it has a very high melting point. The same applies to the boiling points of water. Water has a boiling point of how much? 100 degrees Celsius, whilst methane boils at 18 degrees Celsius. It turns into a gas. No, these are not boiling points. Let me do this. For methane, it boils at negative 164. Negative 164 degrees Celsius. It has already turned into a gas. Imagine. This one, negative 33 degrees Celsius. This other one, negative 61 degrees Celsius. So you can see the difference in the boiling and the melting points between these other molecules that have almost the same molecular mass with water and water itself, which has just a mass of 18. It is melting at 0 degrees Celsius and boiling at 100. And you can see the large range at which water can stay as a liquid. That means it is essential for supporting life. Because imagine if a human being had ammonia in their bodies, and then the temperatures in Zambia are reaching 34, 40 degrees Celsius. That means people would have been boiling. If it's 0 degrees Celsius, you feel it's cold, but someone has already boiled. But to support life, the human body is made up of water. Why? It's because of this wide range, this big range of temperature that water can remain as a liquid. Are we together there?
Yes.
Okay, so that's about the melting and the boiling points of water. And another thing that we can look at is water being a universal solvent. Okay, so this is a very common statement. Water is a universal solvent. Water is a universal solvent. Universal solvent. Like that. So why do we say water is a universal solvent? This is because due to its polar nature, a lot of substances that exist on Earth, a lot of polar substances that exist, they are able to dissolve in water. And hence, it is known as a universal solvent. It's because of a variety of other substances that are able to dissolve, a variety of solutes that are able to dissolve in water. And how is it able to do that? It's because of the same charges, the partial charges that develop around the water molecules. Let's say, for example, we have sodium chloride. What is the chemical formula for sodium chloride? Or if I want to draw the bond for sodium chloride, or how does it exist? Anyone who can give it a try? Common salt, sodium chloride. How does it exist as a compound?
Well, I think it's NaCH2. Cl. I mean NaCl2.
Okay, NaCl2. Chlorine is in group 7. It only wants one electron, whilst the sodium is in group 1. It can only lose one electron. So the 2 there is making everything wrong.
It's NaCl.
Okay, so it's NaCl, and the Na is positive while Cl is negative, right? Am I correct?
Yes.
Yes, because the sodium is losing one electron and donating it to the chlorine. So the chlorine is becoming negative, or rather the chloride, since when it's in a bond, we call it a chloride. Uh, it is losing one electron to the chloride. Hence, it's becoming positive, and the chloride is becoming negative. So when you put salt in water, what or how does this salt actually break down into simpler components? It's because we've said water has two sides. There is this and that, like that. Partial positive here, and then partial negative from there, like that. So this, or how is the water going to surround this sodium chloride? It is going to be like this. You're going to have your sodium here, which is positive, and you're going to have your chloride, which is negative in nature. And remember, water is having what? It is having partial positive and partial negative charges. So these partial negative charges are going to get attracted to the positive charge of sodium chloride, which means the hydrogens will be outside there like that. Even here, there'll be another one. The hydrogens will be outside like that. Here, there'll be another oxygen. Like a lot of oxygen molecules will surround the sodium, hence separating it from the chlorine like that. Even here, hydrogen there outside, hydrogen there outside. Then what about the chlorine? On the chlorine, the opposite is going to happen. Because it is negatively charged, the partial positive charged parts of the water molecule are going to get attracted to the chloride atom there. Hence, we are going to have hydrogen there, another hydrogen there, then the oxygens, since they are negative, they are going to be away from the chloride, like that. You have the oxygen there. Even here, the oxygen is outside, like there, like that one. And by the end of the day, these types of interactions are going to separate the whole compound of your common salt, which is the sodium chloride. It will become one chloride here surrounded by uh, partially positively charged hydrogen ions, and one sodium here surrounded by partially negatively charged oxygen ions. Are we together there?
Yes.
So that's how the phenomena of dissolving takes place. It is like this. I don't know if they might bring this, but I've seen somewhere. I checked the paper, but not from it was from I think UNZA. Yeah. They brought a diagram showing them to say which one is the correct dissolving of sodium chloride. And they included different diagrams. So we should know to say the positive is always getting attracted to the negative, whilst the negative is always getting attracted to the positives. Hence, we are having our compound dissolved, or our polar compound or our charged compound dissolved like that. Okay, so the last one, I don't think we'll finish. Let me just talk about the last property for today. Let's talk about the cohesive properties. Cohesion and surface tension. So what is cohesion? Who can define cohesive forces or cohesion? Just the word cohesion. Anyone who can give it a try?
When water molecules attract each other.
Okay, so cohesion is the ability of a molecule to attract more to a molecule of the same kind. So water molecules attracting to water molecules due to hydrogen bonding is what we call cohesive forces. The ability of molecules to attract more to molecules of the same kind, which means molecules of the same properties or of the same atoms or characteristics. I don't know, but just the same uh, property. So water molecules can actually uh, attract or interact with each other more than they can interact with air. If you put water in a cup, let's say there's a cup here, and you put water, you're going to find that the water molecules that are in this cup, they're going to be interacting with each other more than they are going to be interacting with the air that is above the water level there. And by so doing, this force of attraction is actually very strong that it is going to form a skin. It's not the human skin. Please don't misquote me. It is going to form like a film-like skin on top of this water. And that uh, skin or this film that is formed on top of the water level at the air surface here is what we call high surface tension. Water has high surface tension. And due to this fact, that's why you can see that a lot of things, if you get something which has a relatively lower density and you just throw it in water, it is going to float on top of the water without sinking. Why? It's because there is a tough film that is going to be formed on the water air interaction point here. The water molecules are going to be interacting with each other more using the hydrogen bonds more than they are able to interact with the air that is above that cup. Hence, causing what we call high surface tension. And I have a diagram for what I'm just talking about, I think. Let me check it out. Yes, this one. You can see to say they've put this car, I don't know if it's like a pin. You just put it on top of the water and it's not sinking. It just remained on top here. It is also the same reason some insects are able to walk on top of the water. Have you ever seen a mosquito sinking in water? Here is one, and you can see here, even the way it is looking, Mama side zoom. It is looking like it is standing on a plastic. Aye. Those who are able to see properly, those who don't need glasses, you can see to say where they are to my legs here. It is looking like it is standing on a plastic, but no, it is just water. And this is what we are calling high surface tension. It is the one that is causing a lot of materials to float on top of the water, especially these that are relatively lower density, especially insects. You'll find such questions in your multiple choice questions to say what causes insects such as, or what causes uh, little creatures such as insects to be able to walk on top of the water? It is the surface tension. There is a tough film which is looking like a plastic they are forming on top of your water air reaction point. Are we together there?
Yes.
Anyone with a question? Anyone who is lagging behind or who feels they are a bit behind?
Sir,
Yes.
I didn't understand on universal solvents on the attraction part of the negative and the positive when we draw the part for sodium chloride.
Oh, so you are dragging us a bit behind, but let me just check what you're talking about. Oh, you're talking about this diagram, right?
Yes.
Okay, so I said a water molecule has partially positively charged parts and the partially negatively charged parts. And if you look at sodium chloride, it is a molecule which is, or it is a compound that is formed through ionic bonding. And it involves a complete transfer of electrons. Therefore, it has full charges, full complete charges. Sodium becomes positively charged, whilst chloride becomes negatively charged. And when you throw common salt, which is sodium chloride in water, how is it going to dissolve? It's because the two atoms that are present in sodium chloride are going to be separated by the surrounding water molecules. And how is the separation taking place? Is the negatively charged parts of water are getting attracted to the positively charged part of your salt, whilst the negatively charged parts of your salt are getting attracted to the or the partially positively charged parts of your water.
Thank you, sir.
Okay, so after cohesion, there's also, or after cohesion and surface tension, I hope you've understood the importance of cohesive forces and also surface tension. And the next thing is what we call also another type of force, which we call adhesive forces. Adhesive forces or adhesive forces that okay, so uh other than just possessing cohesive forces, water molecules also possess what we call adhesive forces. And these adhesive forces are going to lead, as we're going to see in the next few minutes, to what we call capillary action. So, what are adhesive forces? What are adhesive forces? Anyone? Anyone to just give it a try? If you are able to define what cohesive forces are, adhesive forces are the opposite of adhesive forces. I mean, adhesive forces are the opposite of cohesive forces. So what do you think is a cohesive, or I mean, an adhesive force? Okay, so adhesion is just the attraction between these water molecules that we've been discussing about all night, uh, and different substances. So that's what we call adhesion. The ability of a certain type of substance to be able to attract, to interact to a substance that is made up of a difference, I mean a different uh, uh, atomic composition, or rather different compound entirely. So mostly you find that these water molecules, when you put them in any container, they're able to interact with the charged parts that are on the surfaces of the container. And that's what we call adhesion. And the same applies, I'm sure you've seen before. There's a lab. I don't know if you've studied labs where you can actually test the capillary action. You put water in a bucket like this, or in a dish whatsoever, and then you put two capillary tubes. You just put a capillary tube there, and then maybe you put another one of a larger diameter there. At the end of the day, you're going to find that the water that is in the cup, or the water that is going to enter the capillary tube, is going to go at a higher level compared to the water that is in the cup itself. Even here, since the diameter is a lot of gravity is going to act here. So it will just rise, but maybe for a reasonable height as compared to this one, which has a smaller diameter. So water is going to rise actually higher than the level of water in this container, which is here. And this phenomena is what we call capillary action. Water is able to interact with the surface of this capillary tube and rise above the level of the water that is in the container. This is what we call a capillary action. And mostly, this is one of the most important reasons why plants are able to carry water from their roots, taking it up to their leaves. They are carrying water from the ground, taking it up against the force of gravity. That is due to what we call capillary action, because water molecules, as they are going up a tree, they'll be interacting with different molecules other than themselves, other than uh, water molecules. Hence, we say the adhesive forces which are causing these sorts of interactions, they are the ones that can lead to what we call capillary action. Are we together there? Anyone with a question up to this point? Anyone with a question up to this point?
No questions, sir.
Okay, so thank you very much, guys, for attending my class. We'll finish when we meet next time. We're going to talk about the high specific heat capacity of water, the high latent heat of vaporization, and also the density and freezing properties of water. We're going to see how water behaves when freezing and why it behaves in that manner. So we'll look at such things and why do we find that in most areas that are very cold, such as Greenland, you're going to find that you have a sea or a lake. You have a sea or a lake, and you're going to find that the whole surface of the lake has actually frozen. It has solidified. It is ice. People are even walking on it. But underground, there is liquid water, and there is even fish living happily ever after. Yes, there's even fish living happily, but there is ice on top of the lake. We're going to see why there are such characteristics that water is able to possess when we meet in our next class, and we also will see why ice is actually able to float on top of liquid water, but it's one thing of the same uh, component. So thank you very much for joining my class, guys. I'm posting this class on Google Drive. So those who are registered, you can go back in case you forget anything. You can go back and rewatch. And those who are not yet registered, please, you can take this time and register with us so that you are able to access all our materials. Oh, thank you very much. I don't know what this name is, but I was guessing it could be Rachel, but I don't know what kind of a Rachel this is. Uh, you are welcome. So those who are not registered, please, you can take this time and register with us. We'll continue with our classes just like this in all 4 courses. And we are looking forward to helping each other in this academic journey. Thank you very much, guys, for coming through. Have a blessed night.